Okay, let us look at a method of multiple scales example again, a different one with oscillations. So let me start like this. That's going to be 0. Now I want you to notice that if I set B equal to 1 and A equal to 1, this is the van der Pol oscillator that we have studied. And if I set B equal to 0 and A equal to -1, then this is a damped harmonic oscillator. So both are included. We will work with both of them together. Let me define the time scales. And so we will say 2, and the T's are the sequence of T, K equals 0 to N. Okay, very good. Now we will say XS is equal to add capital XK of TS times epsilon to the power K equals 0 to N. Very good. That's X. X ds is equal to add diff XS with respect to Tk times epsilon to the power K equals 0 to N. That. It's a bit long, it's okay. Now X dds is equal, we can just copy paste here and save some time, and this is very long, so I will suppress display here. Okay, alright. Now dEA is equal to, substitute x double dot is equal to x dds, x dot equals x ds, x equals xs in dEA, and this is going to be in dE, and this is going to be long also, so I will suppress display, but I'll do a little better than that. I'll expand it out just for the heck of it, not really necessary. Then I will say Taylor epsilon n plus 1, and I will say convert to polynomial, and then now it will be shorter. And you see, this is the order 1 part, and this is the order epsilon part, and that is the order epsilon squared part. So it is growing slowly, but that's all right. Now what I will do is I will just look at the first part, and the solution is a harmonic oscillator. I can think of the solution as A sine T0 plus phi, but A and phi are functions of T1 and T2. And so I will say temp is equal to, and then I will pull this part out, and I will say this is equal to A of T1 T2 times the sine of T0 plus phi of T1 T2, close phi, close sine. Okay, that's my solution. That's the first order solution. Okay, so then I will say, let's see now, I'll say XS is equal to, substitute temp in XS. So I've just inserted it here so that I'll remember later this is what I need. But also I will come here and say dEA is equal to expand, substitute temp in dEA, but after I do that I want to correct for epsilon. Now what I want you to see here in dEA is that only t0 derivatives of x0 are here, but in this equation here we should have, see, for example, for x0 I have a t1 derivative. Okay, I don't yet have a t2 derivative, but when I go to the epsilon squared term, I expect a t2 derivative of x0 as well. Okay, so this is how it will proceed. We will work sequentially. So now we have substituted the order 1 solution and collected for epsilon. I'm sorry that things are a bit longer, but here this somewhere up to here is the epsilon squared term, which is why doing the second order calculation by hand is a bit difficult. Here is the first order part. This also would actually be simpler if I did combined trig, I think, so I will do that now. So now I will come in here and I'll say temp is equal to the coefficient in dEA of epsilon to the power 1, but I will do a combined trig to see if that okay, very good. There we are. Now here is what you need to notice. I have the x1 second derivative and I have the x1, and so this cosine is a resonant term, this cosine is a resonant term, this cosine is a resonant term, this sine is a resonant term. Okay, so these are the resonant terms. We must insist that they are 0. Okay, so let me pull out these things. So let me say the coefficient in temp of cosine, because that's one of the resonant terms. There it is. So what I will do here is I will say E1 is equal to, and E2 is the coefficient of the sine. Alright, and you see this has to be 0, which tells us how A evolves. Okay, tells us how A evolves, the rate of change of A with T1, and because it needs to be 0, right? And this needs to be 0. So if A is not 0, then del phi del T1 becomes 0. So what we have concluded here is this part, which we will substitute, right? So we'll substitute that part here now into the equation, and we will see how that works out. But what is also important is what remains in temp after we set the secular terms equal to 0. And so we say temp 1 is equal to temp minus E1 times this cosine minus E2 times the sine. And we'll look at what is left. Alright, I think we have to maybe combine trig or something like that will work. Okay, here it is. And you see that there is a cosine of 3t0 involved there. Okay, there is a cosine of 3t0 involved there. Will desolve work? Let us see. Will desolve work? Desolve temp 1 for that. Gives me an answer. Okay, so it has found the correct solution in terms of the cosine, and it has the f1 and f2. Because I am not solving an initial value problem, and the sine t0 and cos t0 were included in the original solution for x0. For this reason, I can set these equal to 0. So what I will do here is I will say temp2 is equal to substitute this one equals 0 and this one equals 0 in the above. Okay, so now I've got x1. What happens here? I say xs is equal to substitute xs is equal to substitute temp2 in xs, and I've got x1, and I have some expression for del phi and so on. We'll substitute those two. So I'll say here dEA is equal to expand substitute temp2 in dEA, and let me suppress display, and I'll say dEA is equal to expand substitute, and this phase here, because phi, the derivative of phi with respect to t1 is 0, that means phi is a function of t2 only. So let me put that in here. Phi of t2 is equal to, let me say, phi 1 of t2 in dEA, and then let me say collect epsilon. Although I could have made a shortcut. I will show you what I mean. That didn't work. 1 2 3 4 1 2 3 4, that worked. All right. See, the substitute has to close. I'm sorry, the expand after the substitute has to close. Okay, so there it is. There is an order epsilon term here, but actually the order epsilon term has gone because dt of a1 we should have substituted. So let's do that here, and it will be easier. It will keep things. So here's what we will do. E1 is given. And then I will say solve E1 for this quantity here, just this much, and I will say E1A is equal to control V equals the previous. So I've solved for that also, and then I can come back here and everything is all right. This is all right, good so far. And then over here I have to solve E1A. I substitute that as well. I think I need to do combined trig to clean things up a bit. And just to make sure that I'm not having trouble because some aspect of... Okay, so there it is. It is simpler now, and I still need to do collect dEA epsilon to make sure that nothing is bad and nothing is. You see, everything is order epsilon squared. Very good. Now over here there is still a partial derivative like this. So what I will do now is I will say temp equals substitute E1A in the coefficient in dEA of epsilon 2. Okay, so that's a bit simpler. And now there should be x2 here, and when we look for it we find it, and there should be a second derivative of x2, which is x2 double dot. And so this again is a harmonic oscillator. It cannot tolerate resonant forcing, and so we come here and we say E3 is equal to the coefficient in temp of cosine there it is, and we come to E4 is equal to the coefficient in temp of the sine, and here we stop. Okay, so what happens here is these two must be 0. If they are 0, then you see A is just a function of t1 now. A del t2 is 0, and then when we come here, del phi del t2 is there. No other derivatives are there. So these are the two things that we get, and so our solution therefore is quite simply E1A. We will remember this A does not depend on T2, so this is the amplitude evolution equation. Okay, and you see we had said if A is equal to 1, in that case we have if A is equal to 1 and B is equal to 1, we have the van der Pol oscillator, and if B is equal to 0 and A is equal to -1, we have the damped oscillator. You see both of them are here, and the frequency change is also going to be easy. What we will do is we will say solve E4 for this here. So it's an order epsilon square change, and let's call this E4A, right? So now there it is. It's not that bad, and you see that if B is 0, that means the van der Pol oscillator is not there. Then and if A is 1, then you can see that phi dot has these terms in here. Where this one came from, I'm just wondering. Minus. Oh, I see. If B is 0, I'm sorry, if B is 0, this is not there, this is not there, this is the -1/8, A is 1, that's the damped oscillator. So you know that the oscillation frequency of the lightly damped harmonic oscillator is in fact slightly lower, slightly smaller. So it is something like square root of 1 minus epsilon square by 4 times t, right? So if we do a Taylor series of this, look up the solution for the damped harmonic oscillator and you will see what I'm doing. You see that's the -1/8. The A is 1 and the epsilon squared is not here because this is the time derivative with respect to t2. So d phi dt is equal to del phi del t0, which is 0, plus epsilon times del phi del t1, which is 0, plus epsilon squared times this. And so we are here for the damped oscillator. And for the van der Pol oscillator, we go substitute A equals 1, B equals 1 in E4A, and that's the answer. Apologies. Okay, so that's the van der Pol oscillator. Now this A again is just going to be whatever something it will be. We'll figure out what that is. There are at second order there is a certain amount of non-uniqueness in it, but in any case, as we know, over here there I don't think there is. So over when we look at this one over here, E1A, let me just finish this discussion here. I'm sorry about that phone which rang. Substitute A equals 1, B equals 1 in E1A. When we do that, What is the solution? A equals 2 is the equilibrium solution for the oscillator. So when I come here and put A equals 2, then I find the frequency for the van der Pol oscillator, and we will stop there. Thank you.